All right, here we go, guys. We got 1.10, solving quadratic sum and difference of squares. Technically, this isn't going to be solving, just like the last video. This is, like that, it needs to be darker. This is not technically going to be solving. It's going to be simplifying. Again, as I've said so many times before in the past, solving deals with equations. You're setting up and you're solving for something. There's not going to be any equations here. Challenge, list out, I should just say list the first 10 perfect squares without a calculator. Technically, there's 11 because there's 11 boxes across here, so we're going to do the first 11. So anyway, to find the perfect squares, you multiply the number by itself, which 1 times 1 is 1, 2 times 2, 4, 3 times 3, 9, 4 times 4, 16, 5 times 5, 2, 5, 6 times 6, 36, 7 times 7 is 49, 8 times 8, 64, 9 times 9 is 81, 10 times 10 is 100, and 1 is 121. So knowing knowing the perfect squares is going to be useful doing what we're doing, going into quadratics and whatnot. We're going to go a little bit of review, multiplying the binomials. This is stuff you've done before in the past, so you should know how to do it. If you don't remember the steps, the best steps to follow are FOIL, which is first. Do the first two, or the first in each one, I should say. So this is the first of the part of the binomial. This is the first part of the binomial. So 3x times 3x is 9x squared. We're going to do the outside. So it'll be the outside, which is, if you're thinking about stuff inside or outside, the outside is the outside times the outside, which is 3x times -4, which is -12x. Then we're going to do I, or the inside, which is going to be the inside pieces, the things that are on the inside, which is +4 times 3x, which is +12x. And then we're going to do the last, or the last two, just like we did the first with the f. We're going to do the last, which is 4 times -4, which is -16. What you'll notice when you multiply perfect squares, or the difference of perfect squares, I should say, is these two cancel. What is left now is 9x squared minus 16. Okay, here's where we're going to be going. You knew how to multiply binomials or distribute binomials, whether it be through Punnett squares. You know, you put them all here, you go 3x and 4 and 3x and -4, that kind of stuff, or you did it through FOIL. To get to here, seen this before. Now we're going to be asking you to go backwards. So instead, like if you notice, this right here is very similar to the ax squared. So technically, what we'd be looking at is this would be a squared minus, and that's b squared. And that's where we're going to be going with this, okay? Just to kind of give you a heads up of what's coming ahead. Here we multiply, I'm going to use FOIL again. 2x times 2x is 4x squared. +14x, -14x, -49. Big thing to always remember when you multiply the difference of perfect squares, if the middle two parts do not cancel each other out, positive, negative, you messed up. 4x squared minus 49. Again, very similar case, a squared minus b squared. With a squared minus b squared, meaning that a, okay, squared equals 4x squared, and b squared equals 49. The minus is just the difference. That's the term, the difference. So that's where we're going to be going with this. We should know perfect squares. We should be able to distribute. Now we're going to go backwards in this thing. Okay? So remember these 9x squared minus 16 and 4x squared minus 49, because it's going to be used down here. All right, let's keep it moving. And again, remember, we are simplifying. We are not solving. There are no equations. We will get to a point where we'll be solving some stuff. It just will not be today. Okay, so let's pull up just the difference of perfect squares. What you're going to find is the formula for the difference of perfect squares is A plus B, A minus B. That could also be written, because of the commutative property, you could also write it as A minus B, A plus B. It doesn't matter. It could go either way. It's the equivalent of saying 3 times 2 and 2 times 3. It's still 6. Or negative and negative. It doesn't matter. It's still negative 6. Doesn't matter. Doesn't matter where you put a negative, it doesn't make any difference. So with this being said, if we look at this, and remember how I told you that this is the equivalent of A squared, this minus is consistent, and B squared. And then we're just going to plug it into this type formula. Very similar to the quadratic formula where you had to find A, B, and C, or the Pythagorean theorem where you needed to know A, B, and C and kind of set it up and solve for each one and whatnot. What we need to know is what is A and what is B. So if we look at this, if we see these parts come together, if you will, then we can kind of give them a quantity. Okay, so for what we're saying is that this A squared equals X squared. Well, I want to get A by itself. I need A. I don't need A squared. To do that, I'm going to take the square root. Since they're equal, or their equation, if I take the square root of one side, I have to take the square root of the other. The square root of A squared is A. The square root of X squared is X. That means that A would equal X. Same thing holds true for, but it's different because it's a number. B squared equals 16. When we take the square root of B squared, we get B. When we take the square root of 16, we get 4. This will not be a positive negative thing here. We're not technically solving, so you just want the value. We want the quantity. So don't write positive and negative here. That's only when we're actually solving, and again, why I wrote simplifying. So you need to understand a little bit of a difference of when you use what. So if I look at this and I say, well, if this is A squared minus B squared, well, that equals A plus B, A minus B. Well, my A equals X. And my B equals 4. There's my simplification. There's my factorization. Very similar to the ones up above that we did where we distributed and ended up with this type of answer. You can go back and forth with it. It's just steps. It's the equivalent of walking up a flight of steps and walking down a flight of steps. It's the same spot. You're just going up and down, back and forth, back and forth. Same difference. Number 2 is a little bit different. Why is number 2 a little bit different? The key thing to these things when you use this formula, if this has to be a perfect square and this has to be a perfect square. That's why we talked about those perfect squares. So for instance, this has to be an even. It either has to be 2, 4, 6, 8, 10, something that you can basically cut in half. So for instance, let's say I had A to the 10th minus B to the 10th. Well, that's just cut in half. You would have A to the 5th plus B to the 5th times A to the 5th minus B to the 5th. You're just cutting them in half each time that you're doing this. So basically when this is 2, we're cutting it in half and making it 1, A to the 1. That's the same difference. So we look at this, 2 is not a perfect square, 200 is not a perfect square, but X squared is a perfect square. So we always got to think first word in factoring is GCF. What do they have in common? What's our greatest common factor? Well, the greatest common factor here is 2. So I'm going to pull that 2 out. What is left on the inside is X squared minus 100. Now, we have an A squared squared, which equals x squared, which means our a equals x. And we have a b squared. B squared equals 100, so b equals 10. And that's how that works. So now we're sitting at 2x plus 10, x minus 10. And we go from there. Straightforward. At least it is for me. Okay, number 3, a little bit more of a challenge. Some of these things, you look at them and you're like, oh man, I don't even know where to start with that. Well, the key is GCF. Does 4 and 9 have anything in common? Nope, does not. So the next question is 4 a perfect square? Look up above, it is. Is x squared a perfect square? Look up above, it is. Is 9 a perfect square? Yes, it is. And is that a subtraction sign? So it's the difference? Yes, it is. So we could break these things apart very similar to how we did this. Now my a squared equals 4x squared. So when I take the square root of this, I got a, square root of 4 is 2. Square root of x squared is x. So now my a equals 2x. My next piece is b squared equals 9. So my b equals 3 when I take the square root of them. So now I have an a of 2x and a b of 3. A plus b, a minus b. So my a is 2x plus 3, 2x minus 3. You just plug them in. Again, you're not solving, you're just simplifying. Define your a, define your b, plug it into the formula. Define your a, define your b. Couple of recognition pieces obviously have to happen first. GCF, is 75 a perfect square? Look up above if you know them. It's not. The one is 64, then 81. So 75 obviously would be in the middle, and it's not. So has to have a GCF if we're going to be able to simplify it. Well, 3 is a prime number, so it has 1 and 3 as its only factors. So if we divide both by 3 or pull that GCF of 3 out, we end up with 75 divided by 3 is 25. And then x squared comes down, and this is 1. So now you have to ask yourself, okay, I got my 3, my GCF out. Is 25 a perfect square? Look above. It is. Is x squared a perfect square? Look above. It is. Is 1 a perfect square? We thought it was silly in the beginning, but 1 is a perfect square. Okay? So we're going to pull these apart. Here's my a squared. So my a squared equals 25x squared. Take the square root of both sides. A equals square root of 25, 5. Square root of x squared, x. Donezo. 1. Oh, look how tricky this one is. Is 1. Square root of each side. Square root of b squared is b. Square root of 1 is 1. That's not I there. That's not square root of -1. That's the square root of 1. Do not write that negative. That negative only determines the difference. That negative is only the difference. Do not put b squared equals -1 there. And don't say b equals I. Don't do that. Pay attention. Focus. Plug them in. 3a 5x plus b 1 times a 5x minus b 1. And we're good. Woo! Rolling, rolling, rolling. If we look at number 5, a little bit tricky, but not hard. Okay, so we're looking. We have the difference. Yes, we have a perfect square, a perfect square, a perfect square, and a perfect square. Does 49 and 64 have anything in common? No. Does x and y have anything in common? No. So there's no GCF. So you just got to define your a and your b. A squared equals 49x squared. Take the square root, take the square root. A equals square root of 49, 7. Square root of x squared, x. A equals x. Then we come back, we don't take the negative. That only determines if it's the difference. If you look a little bit below, we're going to start talking about the sum. That's when there's a plus there. The negative just determines this is what we're going to use. It doesn't determine the value technically of that quantity of 64y squared. So our b squared equals 64y squared. Take the square root, take the square root. Let me make that equals look better. Equals. B equals 8y. Let me check the camera, make sure we're in the screen. We are in the screen, but barely. So now I have an A of 7x and a B of 8y. So we're just going to plug in. So we go right here. We know that A plus B times A minus B, we've determined we can use this formula because it's the difference, perfect square. Just plug A, 7x. Put our signs, plus, minus. Could it be opposite? Sure. B, 8y. And you're done. If you try to do that through the noggin, you might get all over the place. If you break it down like a puzzle and start trying to form it out, if you will. Like if you ever try to do a puzzle, you try to get maybe some colors that look the same, or the outside, the rough, the square edges. You try to find something to start with and then build from there. Very similar with this whole simplification and factorization of stuff. Okay, this one's going to give you a little twist here. We got a negative out front. 81's a perfect square. 4 is a perfect square. And x squared is a perfect square, but it's messed up. So we're going to rearrange it a little bit. We need to switch these parts. So we needed to say 4x squared minus 81. That's the same thing, right? That's the same thing. I'm not changing anything. This is positive 4x squared. That's negative 81. We just moved it around so that it looks pretty with our a squared minus b squared. Now we have all these parts that go together as opposed to it not looking the same. And our negatives are in line. So if we think about it, our a squared is 4x squared, so our a should equal 2x. We take the square root of each. Our b should equal 9. And it doesn't matter before plus or minus. We just plug and chug. Our a is 2x plus 9, 2x minus 9. If you follow these steps of defining your A and defining your B, you're going to be much less stress on being able to figure out what to do first. Being able to analyze and focus on stuff and how to break it down is very important. Okay, so we're going to clean the board as always. We've got a lot going on. Get a little wipe down, and then we're going to talk about the sum of two squares. Okay, and we're going to talk about how that is different, why it is different, and how it changes our formula, or what it will be equal to. Okay? So now we're going to roll up, and let me get it all the way. There we go. So I have plenty of space. The sum of two squares, totally different. Sum plus sign now. A squared is still there, b squared is still there. So here's the problem. So we have the sum of two squares. Well, it's the sum, so it's not gonna, those things aren't necessarily going to cancel out if we do things the same way. So we've got to kind of dig back in our brain and think about what did we use? Well, we used imaginary numbers. Remember how we multiply by conjugates with imaginary numbers? So we did this right here. We would say x minus 2i and x plus 2i. Remember how we did that? Remember how we manipulated that around a little bit? It's something similar to this. So we'd say x squared, and then we'd have 2ix, and then minus 2ix, and then minus 4i squared. Here's our middle pieces, cancel. This becomes positive 4. So now we're looking at x squared plus 4. That's what we used to kind of manipulate or move stuff around. We were doing imaginary numbers. We had to multiply by the conjugates to get things, but this was a value before, okay? So now I just called it x. I want to give you an idea of how this is going to work. Same idea, because this I squared that we have in here makes it negative. Unlike before, remember how we had the difference of them. So you had something that looked like x squared minus 16 with a difference of them. Well, the problem with, now that this is a positive, okay, this is a positive, this isn't a negative, I need that I squared that is equal to negative 1, I squared equal to negative 1, to multiply by that negative, if you will, and then turn it into a positive. So that's where we're going to go with these. Just stay with me, follow with me, and hopefully we'll be fine. We will see. And there's, remember also how I had order of all this stuff is very, very important. So the formula, the equation, if you will, is A plus B and then I, and then A minus BI. The only thing you're doing different is you're putting an I after the B. That's all you're doing different. Okay, so we're still going to define the same things. We're going to end up with something that looks like this, A plus BI, A minus BI. That's what we're going to look for. We, like before, need to know A, we need to know B. The positive and negative, the parentheses, and the I's, they're not changing. They stay. When you're dealing with the sum, crucial identification. So, our A squared equals x squared, so that means our A equals x. I'm not going to show all those square roots at this point. After all that, you can go back if you need to. B squared equals 25. That means the square root of 25 is 5. That means our B is 5. So we're just going to plug in. We have x plus 5i, x minus 5i. That's it. No more, no less. No more thought process, no more, no less. There it is. Pretty straightforward. Let's do the one below, okay? This one, this is a perfect square, and this is a perfect square, and this is a perfect square, and it's the sum, so we need to know that we have the I in there. Unfortunately, to factor these things completely, you always have to think GCF first. GCF. Well, these things have a GCF, and that GCF is 4. That's pulled out. Is 25 still a perfect square? Absolutely. Is x squared still a perfect square? Absolutely. It's still the sum, didn't change that, and 1 is a perfect square as well. So we have a squared equals 25 x squared. Square root of a squared is a. Square root of 25 is 5. Square root of x squared is x. So my a is 5x. B squared equals 1. Square root of b squared is b. Square root of 1 is 1. So we just plug in a, 5x, plus b, 1i. I don't necessarily have to write that 1 there. We know that there's a 1 there. 5x minus I. There's a 1 here. Okay? You don't have to write it no different. We don't do this plus 3. We just write x plus 3. We don't write the 1 there. So, but you need to understand that b value is 1. But you don't have to write it. If you want to write it, it's not wrong. But you don't have to write it the same reason we don't write this. We just write x plus 3. Okay? We don't write the 1 because it's not necessary. All right? So let's do 8. Let's come up to 8. 8, a little bit more of a challenge. When you see things like this, where there's multiple x's involved, more than likely an x is going to come out. That's my GCF. X to the third divided by x is x squared plus 49x divided by x is 49. X perfect square. 49 perfect square. Square root of x, x. Square root of 49, 7. The plus tells me I have to have that I. Then you're just going to write the same thing except with a negative. And you're done. When you distributed all that out, you're going to get right back to there. This one is fine how it is. Unfortunately, I don't like it written like that. I like to put these in what you call standard form or standard order, if you will, where the largest exponent is first, and then it kind of goes from left to right down. If you write it like that, it looks better, it makes more sense. Unfortunately, we pulled that x out, but these aren't perfect squares. So we got more of a GCF. Oh, sorry. I wanted to write a 4 and I wrote a 9. Now our GCF is 2x. And now what's left inside that doesn't have anything in common, 4 doesn't have anything in common with 9, and there's no x between the two. Difference of perfect squares? No. Sum of perfect squares? Yes. Can we follow this same protocol? Absolutely. Our a is the square root of 4ax to the 4th. So for instance, you'll have 4x to the 4th and the square root of that. Again, just like we take the square root of x, you basically take half of it. You're going to take half of this. This is 2x squared. Okay? That's our a. A squared equals, so a equals 2x squared plus square root of 9 is 3. 2x squared, square root of 9 is 3. What did I do wrong? I. Gotta put the I in there. That's what the plus tells you to do. Please don't leave the I out. Please don't leave the I out. Sometimes you should put the I in first. Build your brackets out so that you know that the I actually exists within them. It's very important that we be consistent with how we're labeling stuff. The next one is even trickier because now we have like this bunch of whatever for number 9. It's like X and Z's and Y's. The first part doesn't have a number, so obviously 9's not going to come out. So what is in common? The only thing that both of them have in common is this Z. So we take a Z out, and what's left? X squared plus 9y squared. Okay, crucial thoughts. Perfect square root, perfect square root, perfect square root, plus. So we have to have our A plus BI, A minus BI. And this is our GCF. So we're just going to replace all these things as we go along, piece by piece. So our GCF is Z. Our A is x squared, or a squared, I should say, is x squared. So our A equals x. X. I doesn't change. I doesn't change. Our B squared equals 9y squared. That means our B equals the square root of 9, which is 3, square root of y squared, which is y. So this is 3y, 3y. Here's the only concern with this. Technically, in order, you should have your I next to your letter. Remember when we did this, we'd have number and I and then the square root? Same thing, we have number, then I, then the variable. And that's the order of these things. That's how they need to be written. Okay, very important order. mathematics. Order is important. Okay, let's keep it moving. Let's do the next one. Does 25 and 64 have anything in common? Nope. Does x to the 6 and y to the 6 have anything in common? Nope. So what are we going to do with this bad boy? We know that this is a perfect square, 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 and it's the sum of. So we know we're going to have a plus bi, a minus bi. That's our formula. We just need to know what b and y and I and all those things are. So let's define them. A squared equals 25x to the 6. When you take the square root of this, you get a equals 5. So the square root, again, square root of x squared is x. You basically cut it in half. That's why the exponents have to be even. You cut them in half. They're divisible by 2. If it was 3, you couldn't do that. Couldn't take the perfect square root of 3. That's why you gotta take the GCF of the x out first. Now you can do perfect squares. You can cut 2 in half. Here we're going to cut x to the 6 in half, and it's x to the 3. If we look for our b, b squared equals 64y to the 6th. When we take our square roots, we find out that our b is 8y to the 3. Make sure that's in the camera lens while we're rocking and rolling. Oh, just barely, but we'll turn it, tweak it a little bit. There you go. Make sure we're good. So we know our A, we know our B. Now it's just stick it in there, man. Here, 5x to the 3, 5x to the 3. Done. Plus, minus 8y to the 3, 8y to the 3. You don't have to be a genius about how to do these. What you need to be able to do is recognize and be able to take things apart and then understand where they go. No matter where you are in life, you're going to need to know how to break stuff down and then implement it in some way or another. So while this might not be the most exciting stuff in the world, and it might be something that you're like, when am I ever going to use that? It's not necessarily you're going to use this exact type of thing in life, but the application of its model or of its effort will be there. You'll need to know how to dissect things and then put them back together in order or some form of which will be useful for you. I hope this is helpful. I'm out. Peace.